there. I'm going to go over the analysis of variance, ANOVA, and discuss how to calculate, how to go through the steps, and how to write the results. Now, this is one of the more complicated analyses, so I think this is an important chapter for you to do lots of review of and to make sure that you're truly understanding what's going on. There's a lot to it. So first and foremost, let's kind of just look at what we have learned so far, because this is getting towards the end of the semester and you will have a final exam coming up. So we learned descriptive statistics, which was, our measures of central tendency, our measures of variability. We've been working through inferential statistics. We learned the one sample t-test, independent t-test, and related sample t-test. And now we're working on the one-way ANOVA. There's what is called the between subjects and within subjects. For the sake of this class, you're really only going to learn the between subjects ANOVA, which means it's the same thing as the independent t-test, except for you have more than two groups. So it's different people in each of those groups. And then we're going to learn correlation and regression, and also the two different chi-square tests, so that you will be prepared for the final exam. So let's look at analysis of variance. So remember, variance is basically the dispersion of scores across a distribution. And so with this, we're using the variance instead of the mean differences. So your textbook says analysis of variance can be used to evaluate the differences between two or more conditions, but in this case, I would say just more than two conditions. So the t-test is very limited to two conditions, whereas with the ANOVA, we can actually look at more than two, 3, 4 different conditions. So it is gives us a little bit more of a comparison. So you can actually use an ANOVA if you have two different conditions, but the t-test is simpler. So I would always say go with the simplest calculation. But when you have 3 or more conditions, you definitely want to use an analysis of variance. So there's a lot of language with ANOVA that kind of changes a little bit. So we had already kind of been introduced to this with the independent t-test when I talked about factors. So ANOVA talks about factors a lot because of the fact that there's lots of different types of ANOVAs out there. There's like a one-way ANOVA where only one factor is tested, or there's a two-way ANOVA where there's two factors. And so that's why the term factors is used. You won't be learning the two-way ANOVA, but it's good to know that that's a possibility down the road if you're doing some research. So how the participants are observed across the levels of the factors is going to determine whether we are looking at a within subjects design or between subjects design. Now remember, the within subjects design is same people in each of the conditions, right? Whereas the between subjects is different people in each of the conditions. So your test is independent, basically. So we're only going to work through the between subjects design. Although chapter 11 does have the within subjects design, I'm not teaching that to you because there's just not enough time in this class. And it is a bit more of an advanced research analysis. So we're going to focus very specifically on the between subjects design, which is called a one-way ANOVA. So there's lots of different notations with ANOVA. And they are used a little bit differently depending upon you know, what you're used to. Like, for example, we always kind of said before that capital N, as is shown here, is the population size. But with ANOVA, capital N is actually a notation for the total number of scores in the entire study. So if I have 10 people in 3 different conditions, my capital N is 30. So because there's 10 in condition 1, 10 in condition 2, 10 in condition 3, you add that up and there's 30 participants in the entire study. And then we use things like the sum of X, subtext, I put K, so it's usually sum of X for group 1 or sum of X for group 2 or sum of X for group 3. It just specifies which condition that sum of X is for. And now there's what is known as the sum of XT. And that's just the sum of all the scores in the entire study. So if you have 3 groups and you have a sum of X for group 1, and then you have a sum of X for group 2, and you have a sum of X for group 3, if I was to add those 3 together, if I had 3 groups, that would be my sum of X total. That's what sum of X total would be. And K is just the number of treatment conditions or groups. And this was the same as it was in the independent t-test when we were looking at like the HOV, when we were looking up a critical value for that. So that's and kind of K is just a common term for the number of treatment conditions. And then N in this case is just the number of subjects in a group. And we put K here because for each of these groups, there's a sample size, N of 1, N of 2, N of 3. So it's the sample size for group 1, the sample size for group 2, the sample size for group 3. So K is just which group specifically. So when you see these notations, you can kind of get an idea what they are. There's lots of notations with ANOVA, so it's very important that you have your notations down because you're going to be using things and inserting them in different places all the time. So you want to use notations effectively. So some other notations that you're going to be seeing is the sums of squares notations. So in the past, we've just had sums of squares, like sums of squares for group 1 or sums of squares for group 2. But now we have 3 different types of sums of squares. And so we'll have the sums of square total. So basically, we take a sums of squares for the entire study. So if you have 10 scores in group 1, 10 scores in group 2, 10 scores in group 3, you just basically do a sums of square on every one of those scores as if they were all one group all together. Okay, and then there's the sums of group error, which is also the sum known as the sums of square within groups. And we'll talk about how that's calculated. And then there's sums of squares between groups. So there's these 3 different sums of squares that are going to be very important for calculating ANOVA. And then last but not least, but remember, ANOVA is analysis of variance. And so instead of them using S squared, like we've all known for so much time, for some reason, ANOVA decided to change this and they call it mean square. So we know that S squared is sums of squares over degrees of freedom. So this is basically the same thing as mean square. That's all it is, really. It is the variance. Okay, so now that we have kind of those basic things down, we can kind of look at how we calculate ANOVA. So the ultimate calculation to calculate what is called the F ratio or the F obtained is to do the mean square between groups divided by the mean square error, which again, remember, it's basically S squared between groups divided by S squared error. Because remember, mean square means the same thing as variance, as squared. So hopefully that'll kind of help you out a little bit to connect those. But you're going to be seeing MS because that's the notation with ANOVA. So this is how we get our F obtained. It seems simple enough, except for there's quite a few steps involved in this. And the nice part about ANOVA is you get to use a table. Whenever I get to use a table, it makes me happy, and I feel like it simplifies information for me. So there's less having to memorize equations if you can use your table. Okay, so and we'll talk about that as we do it. Okay, so before we start learning actually how to calculate ANOVA, we do need to talk about the assumptions ANOVA has. So the assumptions are the same as the independent t-test. We're going to assume normality. For those test results to be valid, we need to assure these assumptions are met. Normality, so basically either we have sample sizes of 30 or greater, or the sample was taken from a normal population. We're going to use random sampling, and that's typically stated in the research scenario. Independence, meaning that there's different people in each of those groups and they're not influencing each other. And then of course there's homogeneity of variance, basically meaning that the variances are not extremely different. So, and with this, I know it seems complicated because before with independent T, you only had two groups. And so you have the larger variance divided by the smaller variance. It's the same thing with ANOVA. Even if you have 5 different groups, whichever one of those groups has the highest variance, you put that in the numerator, and then whichever one of the groups has the lowest variance, you put that in the denominator, and that's how you would calculate that homogeneity of variance. So here's an example of what a one-way between subjects ANOVA would look like. And so I often just say ANOVA, and is when I just say ANOVA, it means one way between subjects ANOVA, or one way ANOVA, meaning there's only one independent variable, and it's between subjects, meaning there's different people in each of the conditions. So in this, researchers, as you can see, are examining driving performance under 3 different cell phone conditions: driving with no cell phone, talking on a hands-free, and talking on a handheld phone. So, so there are 3 different cell phone conditions, and specifically in this case, there are different people in each of those conditions. So similar to before, we have our hypotheses, the null and the alternative hypotheses. Basically, you're not going to have a hypothesis that says one is higher than the other because you have more than 2 groups. So it could vary back and forth, those means. So basically with your alternative is just there's going to be some difference in driving performance depending upon which cell phone condition people are in. So it could be that all the differences, all the means are going to be different from each other, or maybe just one mean is different than the other means, depending upon what the results show. So it's a very vague hypothesis, and it's never a directional, because ANOVA, if you remember, we have variance, it's analysis of variance, everything's squared. So everything's going to be positive. So our distribution in general for ANOVA is a one-tailed distribution. No matter where we put that critical value is going to be on the right-hand side because our ANOVA is always going to be positive. So here's the data. So we have, clearly we have 5 people in the no phone condition. We have 5 people in the handheld condition. And we have 5 people in the hands-free condition, right? And it looks, if you really look at this, they're looking at scoring performance, like maybe who scores higher on performance. So as you can see, these numbers are higher. All of these are, meaning basically their performance was better. So we're not talking about how many errors or anything, it's just performance. So to give you kind of some context of what is going on with this. So we have 5 in each of those 3 groups. So what we're going to want to do is set our criteria. Well, because our obtained test statistic relies on the variance between groups. So remember, it's MS between groups, and then the variance within groups, or error. So that's error, if you remember. We have 2 different degrees of freedom that we need to use. So we're going to use, basically in this numerator, the degrees of freedom between groups. That's what we call it, between groups. And that is K minus 1. And then in the denominator, it's capital N minus K, and that's the degrees of freedom error. So if we think about it, K minus 1 is the number of groups we have, minus 1. Well, in this scenario, we have 3 groups, right? So 3 minus 1 is 2. And then we have N minus K. Well, capital N is, remember, how many people participated in the entire study. So we have 5 here, 5 here, and 5 here. So our N equals 15, right? So this would be 15, and remember how many groups? K is 3. So 15 minus 3 is 12, right? So we're going to be using 2 and 12. So bear with me a second while this clicks through. We're going to go ahead and go back into the back of the textbook, and this says B3, but ignore that because it's actually C3 now because of the updated. I don't know why they changed those tables, but it's C3, and you'll notice at the top it says critical values for the F distribution. So now we have 2. So part of the reason why I put this like this, 2 and 12, is because in the textbook, this says numerator, and this says denominator when you're looking it up, okay? So if you look at the very top, it says degrees of freedom numerator. And if we're using 0.05, and you can ignore the 2-tel because the ANOVA is always a 1-tel, we're going to look up 2. And then where it says denominator on that very first column, you're going to go down and you're going to find 12. And if you'll notice, there's a light colored, light face number, and there's a bold face number. Because we're using 0.05, we use the light face. So at degrees of freedom 2 and 12, our critical value is 3.89. So basically, our test statistic has to fall at 3.89. So F critical value equals 3.89 or higher. So anywhere out here, and right at this is 3.89. So it has to be further over than that to be significant. So that's step 2 of our hypothesis testing. Now we need to get started on all of the calculations necessary for obtaining our F obtained. So there's a lot of calculations. And this is what I do as far as the basic calculations. You know, I create basically this legend of information. So this is a basic legend that is related to each of these samples separately. So we have our sample size in each. Here's our sample size for each sample. And then we add up the scores, and here's the sum of X for group 1. So 4 plus 3 plus 6 plus 3 plus 4 is 20. And then we have that same thing, the sum of X for group 2 and the sum of X for group 3. And then I get my means for each group separately, okay? And then we need to get our sum of X squared for each group separately, meaning 4 squared plus 3 squared plus 6 squared plus 3 squared plus 4 squared is 86. Okay, 0 squared plus 1 squared plus 3 squared plus 1 squared plus 0 squared is 11. So those are the sum of x squareds for each of the groups separately. Then I use those and I get our sums of squares separately for each group. I know this is a lot of work. This is where it gets very important. When you're doing these calculations, use notations and have them in an organized manner, because it's really easy when you start going through this and you're using information over and over again. It's really easy to accidentally plug the wrong number into the wrong location. And write it down. Don't rely on just saving everything in your calculator, because the calculator shows you things without notation. So that means you're increasing this risk of putting the wrong number into the wrong equation. So once we get all these basic calculations, then we can start working on kind of our combined information. So that's where this legend comes in handy, this little bottom legend. So I have my sum of x total. Oops. So that's basically, I take the sum of x for each of these scores here and I add them up for each of the groups. So 20 plus 5 is 30. My total sample size or total number of participants is 15. So 5 plus 5 plus 5 is 15. Now you have this new one, sum of x squared total. This is basically, if I was to take every score in the entire study, square them separately, and then add them all up. That's what 106 is. But there's an easier way. If you're getting your sum of x squared for each group separately, just add those 3 sum of x squareds up. So 86 plus 16 plus 9 is 106. So this is where it's important to use notations and write each little component down so that you can just start plugging things in, because you're going to be using things in different equations multiple times. So now that you have those basic calculations, and remember we have k equals 3, we can actually start working on what is called the ANOVA table. So I'm going to go forward really quick and show you what this ANOVA table looks like. So we have between groups information in this first row here. Then we have our error information in this row here, and then our total information here. So this is an ANOVA table. I always kind of get that ready to go. So first thing I do is I work on the sums of squares total. So basically is what I'm going to do is use this equation here, which is, I'm going to put it like this, so it seems it is the sum of x squared total minus the sum of x total squared over n. That's basically what this is. So that means you're going to plug in this number here. This number is going to go here. And this number is going to go here. So 106 minus 30 squared divided by 15 is 46. So we have our sums of squares total ready to go. Now, once I get that, I'm going to skip forward ahead. I usually plug that in right here, SS total, because if you notice, here's my sums of squares column. Here's the degrees of freedom. We already had that. So the between groups was 2, the error was 12, and then the degrees of freedom total is capital N minus 1. So we have 14. And the key here is if you add this, the between groups degrees of freedom to the to the error degrees of freedom, you should get your N minus 1, the total. So it's a good way of checking your work. Okay, so now we've got the sums of square total. We're going to do the sums of square error, so SSE. And that basically is you take your sums of square that you calculated for each group separately and you add them up. So sums of square error is basically SS, the sum of all of the SS is what it is. So we get 16, okay? I plug that into my table right here, 16, okay? It's as easy as that. Just plug it in. Now we're gonna go and we're gonna do the sums of square between groups. Okay, I only give you equal sample sizes in this class. So I'm teaching you the method that is the easiest based upon equal sample sizes. And so because we have equal sample sizes, we can use the means to calculate our sums of square between groups. So if you'll notice, we have this equation. It looks like this is SS means, right? But is what we want to get is SS between groups, okay? To get SS between groups, we have to multiply the sample size times the sums of square means. So that's the key. As often as what I see students do is calculate the sums of square means, and then they forget, oh, that's not the sums of square between groups. So the sums of square between groups is n times the sums of square means. Don't forget, once you get this, you have to plug it into the final equation. So to get your sums of square means, you basically just do a sums of square on the means. Pretend they're like raw scores. So we have m of 4, m of 1, and m of 1, right? So if I look at sums of square means, it's basically the sum of m squared minus the sum of m total squared divided by k. So I'm going to take each one of these and square them. So 16, 1, and 1. Then I'm going to add those up, right? 16, 17, 18, if you notice. I'm going to plug that in right here. See how that's right here? Then I'm going to take the sum of the means in general. So 4 plus 1 plus 1. So 4, 5, 6. I'm going to plug that in right here. So we end up with basically, so we have 18, sorry about that, minus, then 4, 5, 6, 6 squared divided by, and k is 3, right? So 6 squared is 36, divided by 3 is 12. So if you'll notice, 18 minus 12 equals 6. So this final answer equals 6. Then you're going to plug this in. So you have to multiply that, put that into the parentheses, and multiply it by the lowercase n. Again, this equation can only be used with equal sample sizes. So how many were in each of the groups? There was 5 participants in each of the groups. So we multiply 6 times 5, and that's 30. And that's our between groups sums of squares. So here's that. So there's a couple different things we can do. We can make sure that we're calculating things right by taking 16 from 46, and that should get us 30. Or we could do 30 plus 16 and get 46, right? So the problem is, and this is where I highly stress, don't cheat this. Don't automatically just go, oh, I'm going to get the between groups and get the error and then add those up. Because the problem is if one of those is wrong, you'll never know you got it wrong. But if you calculate each of these sums of squares separately, but when you add the between groups and the error together, if they are not equaling the sums of square total, you know you did something wrong. So this table helps us to catch errors. It's something that we don't have the benefit of having with an independent t-test. So all of a sudden, if let's say I got 30 for the between groups, or how about I got 28 for between groups, 16 for error. Okay, so that means I would have got 44 for my if I would have added up, I should have got 44, but I got 46. And I go, oh, something went wrong because I should be getting 46, but I only added up to 44. I can guarantee you your error is probably right here in the between groups. You probably forgot to multiply by the sample size. So it's a good way to catch those errors. Once you get your sums of squares for each of those, the between groups, error, and total, and then you filled out the degrees of freedom for those 3 rows, and it's always in this order. Between groups is the top row, error is the middle row, and total is the bottom row. We can just use the table to calculate things. So instead of you like remembering these equations, you just remember how to use the table. Put a division symbol here. Put a division symbol here and an equal sign here and here. So 30 divided by 2 is 15. 16 divided by 12 is 1.33. Then think of this as division right here. Here's a division, okay? 15 divided by 1.33. So if you look, mean square between groups divided by mean square error. 15 divided by 1.33 is 11.28. Bam. So that's where the table is really useful, because you can not only check and make sure you didn't make errors in your sums of squares, but you can, instead of remembering all these equations, you can just remember, oh yeah, the table, if I have it set up, sums of squares, degrees of freedom, mean square, F obtained, then it's automatically, you know, like put this division sign here, this division sign here, and this is division between this and this. And that equals our F obtained. So now we have our F obtained, which is a lot of steps, I understand. But the nice part about ANOVA is that you have this table to help check your work. So now we can calculate an effect size. Again, we can go back to this table. If you look, our eta squared is the sums of square between treatments or between groups divided by sums of square total. If we go back, it's this divided by this, right? So this is in the numerator, this is in the denominator. So 30 divided by 46, okay? 30 divided by 46, okay? So if you plug that in, it is 0.65. Now remember, eta squared is a measure of the percentage of variance. So you should never be getting anything that's negative, and you should never be getting anything larger than 1, because percentage of variance, highest you can get is 100%, which is 1, okay? So now we have our entire table, we have our obtained, we have the effect size, like I just said. Now we can actually determine, you know, whether it's significant or not, right? Well, remember, if we go back, our critical value, F critical value, equaled 3.89, if you remember right, okay? Because our denominator, our numerator degrees of freedom was 2, right? And denominator was 12, so that critical value is 3.89. Anything out there is significant. 11.28 is way out here, so it is significant. So once we obtain a significant result, we actually need to find out where the significance is. So this is where we roll into what is called post hoc testing. So I'll kind of discuss what post hoc testing is. So when we calculate our F obtained, it doesn't tell us where things are significantly different. It just says somewhere among all of these groups, there's a significant difference. So if your test is significant, then you have to do post hoc tests to tell us where. So here's kind of a map. Okay, you get your ANOVA, your F obtained, okay? And if your result says to reject the null, that means it's significant. You conduct post hoc tests. If the result is not significant and you retain the null, you stop and you report your APA, okay? So that means that they don't significantly differ. So here's some common errors that I see students make. You do your ANOVA, your overall test result is not significant, but for some reason you do post hoc tests. And then you tell me there's significance between groups. But there can't be significance between groups if there's not an overall significance in your F obtained. So if your test is not significant, you can stop right there. But if it is significant, then you have to calculate post hoc tests to find out where it's significant. And then you kind of weed apart like how that looks. So to get a calculated post hoc test, we're going to use a Tukey's HSD. So Tukey's HSD is this equation here. So Q is a critical value, okay? So Q is a critical value. And that's going to depend upon your degrees of freedom error and what they call the range, which is K. So now you have to go to a whole nother table, and ignore that, it's not B4, it's C4. So it's the table right after your F distribution table, and it's called the studentized range statistic, or Q. There's a little Q at the end of that sentence. If you'll notice at the very top row, it says range. Well, that is basically K. K is range, so the number of groups. And then on the side, it's DFE, so your degrees of freedom error. If you remember, our degrees of freedom error was 12. So we're going to use K of 3, degrees of freedom of 12. The critical value for 0.05 is the light face, right? So it's 3.78. So we plug in that critical value there. And then we use our mean square error. Okay, so Tukey's HSD can only be used for equal sample sizes. But again, like I said, I only teach you equal sample sizes. So that's all you need to learn. So we're going to use our mean square error. If you go back, here's the mean square error. Right here, it says within groups, that's the same thing as error. Okay, so just go back and get that mean square. You plug that in here, and then the lowercase n is how many were in each of the groups. There was 5 people in each of the groups. You take the square root of that fraction and then multiply it times 3.78, which is your Q, and you get 1.95. So that's your Tukey's HSD. But then you're like, well, what do I do with 1.95? All you need to do is check and see, okay, where are your means greater than a difference of 1.95? So is what I do is I look at my means. So here's my mean for group 1, my mean for group 2, my mean for group 3. I just look at all the possible combinations. So I looked at group 1 versus group 2. So 4 minus 1 is 3. That's greater than 1.95, so that's where we have significance. So starring that one. Group 1 versus group 3. Again, 4 minus 1 is 3. That's greater than 1.95. The difference between those groups are significant. But then group 2 versus group 3, these both have the same. So that's 0. That's not significant because it's not greater than 1.95, okay? So then is what I want to do is kind of look at this. Okay, well, what's the pattern? So it looks like people with no phone perform better, significantly better than people with a handheld phone or a hands-free phone, right? So basically that's what we need to implement into our APAs after our APA's statement. So here is our APA conclusion, and this is with post hoc tests. So first and foremost, this first sentence right here is your APA result for your overall ANOVA, okay? For just the overall ANOVA. Analysis of variance revealed there is a significant difference in driving performance related to cell phone condition as F, and we use the degrees of freedom that we use to look up our critical value. 2, that's the degrees of freedom between groups, comma, degrees of freedom error, which is 12. Our F obtained, because it was significant, P is less than alpha. We don't need to say 1 or 2 telled because it's always a 1 telled. And with eta squared equals 0.65. Everything is rounded to 2 decimals. Okay, now there's a period, and now because it was significant, you report your Tukey's post hoc tests. And you report your means so that people can see where there was a difference. So here I put Tukey's post hoc tests show that driving with no cell phone, I provide the mean in parentheses, M equals 4, shows significantly better driving performance than driving with a hands-free, I provide the mean after that one, or driving with a handheld cell phone, and I provide the mean after that one. So if your test is not significant, you would just stop right after this 0.65, and that would end the sentence, and you'd be done if your test was not significant. But because it was significant, then we have to provide the results of the Tukey post hoc tests. So that's how you write the APA conclusion. Hopefully this made sense. Some of the reasoning for doing post hoc comparisons is because it controls for error. It's called experiment-wise alpha, meaning that basically for every test we run, we're running the risk of error. So for every alpha level, we're running the risk of error. So if we did an independent t-test and we let's look at group 1 versus group 2, we're setting an alpha of 0.05. So there's a 5% error between that. And then we did, let's check between group 1 and group 3. Okay, there's another 0.05, okay? And then between group 2 and group 3, and there's another 0.05. So what that does is that it adds together and creates a 15% error. So what we need to do is control for experiment-wise alpha, which is basically the error. And so there's lots of different tests out there. There's Bonferroni, there's Sheffy. These are some pretty conservative tests with less power. Or there's Tukey's HSD, Fisher's LSD, those ones are typically the ones that are most widely used. So if you see these in the text, you'll understand why. There's all these different types of post hoc tests. So ultimately, here's kind of that explanation of what happens with experiment-wise alpha. So remember that type 1 error. It is the probability that your significance is, your conclusion is an error based on setting the alpha level. And like I said, if you look at each of the conditions in t-tests and you look at 2 groups at a time, you would have to run 3 different analyses to find out what we did with 1 overall analysis with ANOVA. So with F, we only have 0.05 risk, so a 5% risk. But with a t-test, we have 0.05 for every single test we'd run, which would add up to 15% probability of a type 1 error. So that's why we run the overall ANOVA and then post hoc test, because it accounts for that potential of error. So overall, ANOVA has the same effects of power as the t-tests. Now, remember, when we're talking about error, it's different than power. Definitely error and power are related, but when you talk about, if you increase sample size, you're increasing power. You're not affecting error per se. Error, whenever I talk about error, it's only related to how you set your alpha level. But power absolutely is talking about the things that make our obtained test statistic larger. So as sample size increases, power increases. You know, as the size of the real effect or the magnitude of the treatment effect, as the differences between the means increase, the greater the power is. But with variability, again, power is inversely related. So if there's a lot of variability in your samples, that means your power is going to decrease. So we often can see that being a problem with getting significance in our tests. So hopefully that made a little bit of sense. I think that it's going to help with lots of practice. I would recommend you looking at the YouTube videos for calculating ANOVA and go through the steps a couple of times with me. And please, if you have questions, come see me during office hours or email me any questions that you may have. This is complex, ANOVA is, so I expect to be hearing from more than one of you, a lot more, because it's complex information.